Hello, I'm Thomas with Geon Technologies, and welcome to the second part of Property Kinds series, Execparam and Allocation. We'll be continuing where we left off on Part 1, so please complete that session before attempting this one. As a reminder, at the end of Part 1, we had our very simple device that could be reconfigured on the fly with new amplitude and frequency using its control params property. It would then generate a set of samples based on its predefined sample frequency and return a number of them in a sliding window. Now for Part 2, we'll be adding the ability to change the number of samples returned in that window, as well as the ability to allocate a preferred sample frequency. We'll briefly sandbox our changes, and then use our waveform to show how usesdevice relationships come into play with allocation properties. This will finish our brief exploration of the lifecycle-related kinds in REDHAWK before we move on to messaging in the next session. Let's start by updating the Sawtooth device. Open the Sawtooth device's SPD project file and Properties tab. Add the new simple property with ID of window and useShort for the type. Set the kind to only Execparam and give it a default value of 100 samples. This will ensure we have our initial value prior to reaching our first configure or allocate capacities call, but still give us the ability to override this setting prior to the parent node starting. Next, add another simple property, SampleFreak. Set its type to float and an initial value of 1,000,000. Set its kind to allocation. This property will give waveforms a hook for changing the sampling frequency prior to connecting and starting its deployed components. Generate all implementations and navigate to the Sawtooth device PI file. Time for some copy-paste from the code blocks. First up, head down to Get Data towards the bottom of the class. You'll recall this is the actual signal generator function. When it's called and a signal has been generated, this function slides a window along the signal and returns those samples. The variable we're replacing is called count. Something we've glossed over at this point is that in an object-oriented sense, properties become public properties on your class's base implementation. Since we have now implemented a property called window, we can replace each of these instances of count with self.window, as you see here, to hook the getData function to our new property. Up at the top of our implementation class, we also have previously defined a property called SampleFreak. We can now eliminate that line so that we use our new allocation property, which, conveniently, shares the same name. As mentioned earlier, an allocation property gives waveforms and components a hook for manipulating your device prior to their own deployment. When that waveform or component is released, the hook is released with a deallocation call automatically. Similar to configuration, implementations support allocate capacities and deallocate capacities methods. And since this is a Python implementation, we get to use the allocate or deallocate _ property name to capture only the property of interest, in our case, SampleFreak, as you see here. Looking at the allocate command, you can see that we are checking two things here. First, does the new value meet Nyquist criterion? And second, is the device already busy? What this is doing is making our device become reserved to one allocation at a time. And while I won't be showing this later, I'll remind you of when you can test it. If this device can allocate to the new value, we keep the value and check if we should also auto-start. For deallocation, we again check our usage state to determine if we should stop based on the usage state. This probably looks like bad logic. We use the started state to drive our usage state, if you recall. So if we're started, we're also busy and would not be attempting to accept a new value. I've left the logic this way though simply to expose you to some of the methods you can use for checking the device or component's state in the event you want to experiment with different ways to determine your usage state, but retain usage state as a means for reserving this device. But keep in mind that self.data needs to be cleared by some means between allocation calls to ensure that the signal is resampled correctly. We're handling this in the stop method, but feel free to experiment. So, it's time for that experiment. Let's see if our allocation actually changes the usage state and modifies properties. Open a terminal and navigate to the Sawtooth Devices project, then start Python. Import aussie.utils sandbox and launch your device as you did previously. Check the usage state using the method shown. You'll see we're idle. Now use the allocate capacities method to allocate a 2 MHz sample frequency. You'll notice it returned true immediately since it passed the Nyquist check and the device was already idle. But if we check our usage state again, we see it's now busy. You're welcome to attempt another allocation. The method will return false. To mimic what will happen during an actual deallocation, I'm calling deallocate capacity with our previous 2 MHz sample frequency value. And again, our usage state is idle. Knowing that deallocation will always call with the associated values is a useful concept to which you'll almost certainly be exposed if you standardize your device to a front-end interface specification. But that whole powerful topic is worthy of a separate discussion, so we're going to shelve it for now. Let's exit the shell and prepare to test this with the real thing. Drag the Sawtooth Devices project to the target SDR to install it in the SDR root, and then open the siggen node DCD file. Here you can see our Sawtooth device instance and a GPP, which will be executing our deployed components. Let's take a look at our Sawtooth device's properties from the node's perspective. You'll notice that all properties are grayed out except our configure and execparam properties, control params and window, respectively. The node can't modify an allocation property unless it's also one of the other kinds, since the intent is for a third party, external to the node, to set the value as it needs. Let's go ahead and set our window to 300. Save and drag the node to the target SDR to install it in the SDR root. Do the same for the controller waveforms project. The controller waveform represents our third-party external user. It already has its usesdevice relationship looking to allocate the ID SampleFreak to a value of 100 kHz and connect that device to its data converter component. If you have been through our Waveform Usage Basics section, you'll be able to quickly find that relationship in this add file. If your Omni services are not running, feel free to use our Restart OmniOrb script from the repository's utilities folder. We'll need the services to actually test allocation on a domain. When you're ready, right-click the target SDR and launch the domain and our siggen node. Once they're up and running, navigate through the domain to our Sawtooth device to look at its properties. You should see the window is now set to 300 and SampleFreak is still the default, 1 MHz. Right-click on the domain and launch the controller waveform. Feel free to have it auto-start. Once the waveform is up, check the properties again. You'll see the SampleFreak is now allocated to 100 kHz per the waveform's usesdevice relationship. Earlier, I mentioned that SampleFreak is a way to reserve this device to a single waveform. Feel free at this time to attempt to launch another instance of the waveform. It will fail because nothing else could be allocated in the system. Also, at the end of part 1, I mentioned that we could equivalently send our configuration commands from the IDE. Let's do that now by expanding control params and setting the amplitude and frequency to 5 and 250 respectively. And of course, now they're listed in bold since the values differ from the device's defaults. Return to a terminal, Python, and import both REDHAWK and Sandbox from aussie.utils. We'll need both to verify our work. From REDHAWK, attach to the domain by its name. Then, from the sandbox, get a line plot. Since we know we have only one app and component running, we can index blindly to the component and connect its output to the plot. However, this component has several outputs, and we're only interested in connecting the data float out, so specify it with the uses port name to clarify what we're intending to connect. Start the plot, and you should see our sawtooth with amplitude 5. Now, not shown here, but feel free to release this waveform using the little red X. You'll see the device automatically stop, go idle, as it did earlier in the sandbox, since the waveform will deallocate capacities as it is released. You'll need to relaunch that waveform if you'd like to see this next feature in action. The domain ensures that all allocated capacities for a waveform exist while the waveform is deployed. If those capacities are lost, the waveform is released automatically. If we shut down the node, moments later we'll see that the domain has released the waveform too. This is how allocation binds your hardware, in the form of nodes, to your end user applications as waveforms. Here I've used the refresh option to give my virtual machine some encouragement, but rest assured the waveform was long gone. We can now close out everything by stopping the sandbox and exiting the session. The rest of the system can be shut down using the console's terminate and remove buttons, and to clean up, simply disconnect and delete the domain from the SCA Explorer once it has been shut down. That brings us to the end of Property Kinds Part 2, Execparam and Allocation. Reviewing some of our key points. Execparam property values are set prior to devices and components initialization. Allocation properties act as hooks for third parties. Allocation properties also are changed prior to those third parties coming online. Loss of capacities will release the waveform. Again, I'm Thomas with Geon Technologies. Please feel free to contact us for more information or in-class training. Thank you for watching.